Hi, everyone. In our next section, 26.2, we're going to be looking at areas by integration. So we get more detail with area, but we start out with a little bit of review. When we write a definite integral, that gives us an area from a to b of f of x dx, right? That's what the notation looks like for a definite integral, but what does it represent? It represents an area underneath that function, right? So if I have my function, this guy is y equals f of x, the bounds of that integral are from here to here, a to b, and that gives me the area underneath the curve. And in that integral, the dx, that's the variable of integration, but what that essentially represents is that like little rectangle that we sometimes kind of draw in there. That dx represents the thickness of that rectangle, that really, really thin rectangle. In the integration activity, it's the delta x that you use in dividing the region up into 8 or 10 or 12 rectangles, or an infinite number of rectangles that are infinitely thin when we use an integral and an antiderivative. Right, and then so let's just do another quick like little review example here, and we're gonna find the area the area under y equals x squared between x equals 1 and x equals 2. So to find that visually, what does that look like, right? Y equals x squared is a parabola that hits the origin. Oops, I missed again. Is a parabola that hits the origin. That's much better. And let's call this 1 and this 2. So the integral is going to give us the area of this region right there. And so we're going to evaluate this definite integral from 1 to 2 of x squared with respect to x dx. Antiderivative, add 1 to the exponent, divide by the new exponent. So we get x cubed over 3. Evaluated from 1 to 2. 2 cubed over 3 minus 1 cubed over 3 equals 7 over 3. 2 cubed is 8, minus 1 is 7. So 7/3 is the exact area of that region. Now, one thing that is sometimes necessary is we can integrate with respect to other variables, and we haven't done that yet. So I'll tell you why that's sometimes necessary. So let's say on this next example, here's my x-axis, here's my y-axis. I want to find the area, not the area down here to the x-axis. I want to find the area underneath, well, I'll say underneath, but really between the function and the y-axis instead of the x-axis. So I want to find that area there from some value here we'll call a up to some value b up there that we'll put right there. Okay, so when I want to integrate, when I want to find the area dropping down to the y-axis, well, my rectangle that I would draw here in this region, my really, really thin rectangle, that I'll sometimes draw reasonably well. That's not bad. But there's my rectangle. Well, now since it's dropped down to the y-axis, we call it dy instead of dx. And in integrating my function, instead of y equals f of x, it's x equals g of y. Oops, that's not an x. X equals g of y. My function is in terms of the variable y instead of the variable x. And so what that looks like is a equals the integral from a to b of g of y dy. And that it's just we're integrating in terms of the other variable. We're dropping our rectangles down to the y-axis instead of the x-axis. So then let's look at an example where we use that integration. So let's say I have the equation y equals 9 minus x squared, and I want to find the area in the first quadrant. Okay, quadrant. That looks terrible. There we go. All right, so what does 9 minus x squared look like? It's a parabola. It's a parabola that opens downward and has a y-intercept up here of 9. So there's my y-axis, there's my x-axis. So here is my parabola. All right, and it continues on past the x-axis, but that's good. There we go. All right, so I just want to find the area in the first quadrant, though, so this region here that I'm shading in red. Okay, and we can do that two different ways, which is awesome. One way is a little bit easier, one way is a little bit harder, but it shows you why but it's helpful to see that they both produce the same result. Okay, so the one way, the traditional way, is we're going to find the area taking the integral of 9 minus x squared with respect to the x-axis, and those rectangles, that region, goes from x equals 0 here up to that value there. If you solve 9 minus x squared equals 0, that is 3. So the bounds of our integral are from 0 up to 3, and that's going to give me the area. So then we find our antiderivative. That's the first step in finding this, in evaluating this integral. 9 becomes 9x, x squared becomes x cubed over 3, and then we plug in our bounds from 0 up to 3. 9 times 3 for the top bound, minus 3 cubed over 3. Cubed, there we go. Minus bottom bound, you can check. 9 times 0, 0 cubed over 3. Bottom bound is going to give you nothing, big old 0. And so we get that area is 27 minus 27 thirds. 9 times 3 is 27 minus 27 thirds, and that is just 27 minus 9, which is 18. So the area underneath that parabola, and that's kind of cool, it's a curvy looking parabola, but the area underneath it is a whole number. Okay, now we're going to do this problem again and make it much harder. You'll see, but it's more practice, but it's showing you that it produces the same result. Okay, so instead of integrating with respect to x, so the dx here, we're going to drop our rectangle down to the y-axis. So notice this green rectangle that I'm adding in here. This is going to be my dy, my slices with respect to the y-axis. We're chopping that y-axis up into rectangles. We can see that we still start out at 0, but it goes up to a y value of 9. So my dy integral, the area, is the integral from 0 up to 9. Okay, we'll come back to the function in just a moment, and we're chopping it up with respect to the y-axis, so my dy rectangles. All right, but what's the function that I'm integrating? Well, it is the equation is y equals 9 minus x squared, right? And if I want to integrate with respect to y, I need to solve that. So I need to add the x squared plus y equals 9. So I'm adding x squared there, adding it there, and then I'm going to subtract the y. X squared equals 9 minus y, and then take a square root on both sides. X equals the square root of 9 minus y. And we get a much uglier looking equation, okay, but that is the function that we are integrating, 9 minus y. So it's the integral from 0 to 9 of 9 minus y dy. Now, to actually evaluate this integral, we need to do a little u substitution. So we saw that once before. We'll see it again. It'll rear its ugly head every once in a while. We're going to set u equal to what's underneath the radical sign right there. Not the radical itself, but just what's underneath it. 9 minus y. And du, the derivative of 9 is 0. The derivative of negative y is negative 1 dy. Okay, so that's our little tiny u substitution. And what are we going to do there? So if u equals 9 minus y, we can, let's see. So I'm going to rewrite my integral now. I'll leave the bounds off for a minute. Inside of that radical, it's just the square root. Oops, but let's write that as u to the 1/2 power du times negative 1. Okay, so the du over here is the du right there, and that negative 1 there, I need to write it on the other side, just like we were, if there was a 2, we divided by 2, so we solve for that dy, okay, which gives us just a negative sign popping up inside of our integral. And then, in addition to that, we want to rewrite our bounds. So if u equals 9 minus y, the top bound, 9 minus 9 is 0, and the bottom bound, 9 minus 0, is 9. which is a little bit weird, but let's see how this all works out. So I'm putting a 9 down there and a 0 up there. All right, I'm a little nervous about what's going on, but let's just keep going. All right, this is a little bit more challenging. We'll do some more standard type problems in a minute. So a equals u to the negative u to the 1/2. Keep our negative sign. U to the 3/2. Add 1 to the exponent. Check that in your calculator if you're not sure. Divided by 3/2. Evaluated from 9 to 0. All right, and when I plug in my top bound, negative 2/3, because that for 3/2 flips up, times 0 to the 3/2 minus negative 2/3 times 9 to the 3/2. Ooh, lots of negatives, lots of fractions in this one. Thankfully, that first term doesn't matter at all. Thankfully, we have a minus negative that becomes a positive. 9 to the 3/2, check that in your calculator. The square root of 9 is 3. Cubed is 27. So this is 2/3 times 27. 27 divided by 3 is 9, times 2 is 18. Wow. Okay. That was a little rough, but we got the same answer. Look at that. 18 up there, 18 down here. Integrated with respect to different variables, evaluated the different bounds. One of them was way easier, way more straightforward than the other. Okay, and that happens in both directions. Often integrating with respect to x is better, but sometimes integrating with respect to y can be better, can be an easier integral to evaluate. Now we get to this next piece where we can find an area between two curves. So not just from a curve down to the x-axis, but rather an area that has a top curve and a bottom curve. And one important thing for us to pay attention to is which one is the top. Right? So in this formula here, this guy here is a formula, we have the f of x minus g of x in that formula. And the thing to note and pay attention to is that f of x is greater than or equal to, which means on top of, above g of x. So the f goes first. The top function goes first. So it's top minus bottom when we do this. And so in the example, we have find the area bounded by y equals x squared and y equals x plus 2. So it's going to be really important to either sketch freehand or type into your calculator the graph of these two functions, because we need to know which one's on top. All right, so y equals x squared, that's just our regular old parabola, this guy right here. Okay, that was a little too pointy, but that's all right. Y equals x squared. And then y equals 2, or y equals x plus 2, excuse me, that has a y-intercept of 2 and a slope of up 1 over 1. And that's what we're looking at here. This is y equals x plus 2. And so what we can see is that the one that I'm circling in green here, that guy's on top. I know the equation I wrote below the other one, but that line is on top. So if I think about how my slice, my rectangular slice in that region looks like, the top of the region is the line, the bottom of the region is the parabola. Okay, so that's really important. Now, so we're going to write our area, our integral, come back to the bounds in just a moment, of the top, which is x plus 2, minus the bottom, which is x squared. That gets integrated with respect to x. Cool. The other piece that we need to do, though, is what are the bounds of my integral? Well, my region starts over here and it ends over there. But how do I get those two numbers? I didn't draw a good scale on here. Well, this is where your TI-89s are going to come in handy. So I'm going to use the solve feature on my calculator. I want to know when the parabola and the line intersect. So when does x squared equal x plus 2? Type that into your TI-89s and see what happens. If you do that, your calculator will spit out -1, x equals -1, or x equals +2. And that represents the 2 points that I have circled there in red. Those are the 2 points of intersection, and those also are the bounds of our integral. Now, you could solve that equation by setting it equal to 0 and factoring, and that would be fine. But use your TI-89s. In a challenging problem like this, it's just quick and efficient to use the calculator for the more basic stuff where you might make a mistake. So we're going to now take the integral, find the antiderivative. X becomes x squared over 2. 2 becomes 2x right there, and x squared becomes x to the third over 3, and that all gets evaluated over the bounds. And again, if you don't like doing the bounds by hand, you can absolutely use your calculator to do this substitution. X squared over 2 plus 2x minus x cubed over 3. Type all that into my calculator, vertical line x equals 2, and hey, it spits out 10/3. Do the same thing, vertical line x equals, -1. Calculator spits out -7 over 6. 10/3 minus -7 over 6 is equal to 9/2, 4.5. So again, the area between those two curves, it's a curvy region kind of with the parabola there, but it's a fraction. 4.5 is the area. Square units is the area of that region. In this next example, we're going to sketch the region again. And it says find the area bounded by this 1, 2, 3, 4 lines in this region. So y equals x cubed minus 3, x equals 2, y equals 1, y equals 3. So those 4 lines, what kind of a region do they create? And we have to use an integral to find the area of that region. So what I'll do first is, what does my cubic function look like? Well, it's this, right? That's my nice looking cubic function, but it's x cubed minus 1, 2, 3. So it's really a cubic function that just is a little bit lower. So there's y equals x cubed minus 3. And then what else do we have? We have the line x equals 2. And I'll stick with blue, I think. X equals 2. Well, here's 1 on the x-axis. Here's 2 on the x-axis. So x equals 2 is this blue line here. So this is y equals x cubed minus 3. This one is x equals 2. All right, keep going. Y equals 1 and y equals 3 are both horizontal lines. Here is y equals 1. And here is y equals 3. Okay, so being able to sketch these regions or put them into your calculator, although the vertical lines, those don't graph very well in your calculator, but that's going to help us to set this integral up. Now that I've got the region sketch, this is one I'll tell you ahead of time. We're going to do this one with respect to y. So we're going to chop this up with dy rectangles like that. And I'll usually, or maybe I'll always tell you whether you're integrating with respect to x or y. I probably will always tell you. But in this one, it's definitely a dy, and the reason for that is the dx one just ends up being a little bit more challenging because of the way this region looks. All right, so how do I set up this area, right? Area equals integral. The bounds, well, this is actually the easy part. The bottom bound is 1, the top bound is 3, because those are the horizontal lines that define my region, okay? And then what is the top function and the bottom function? Well, this guy is on top, because as you number your x-axis, the bigger numbers go this way. So this is the top. So y equals x cubed minus 3 goes first, but we need to solve that for x. So it's x cubed equals y plus 3, or x equals y plus 3 to the 1/3 power. And that goes here, y plus 3 to the 1/3 power. So that's my top function minus my bottom function is just that line x equals 2. And notice it's already written as x equals. So that 2 just goes right there, dy. In this problem, I just want to focus on the setup because it's a different one. We're integrating with respect to y, the dy there. If you do go through the evaluating, you get like a little tiny substitution there. I don't want to get too worn out on this one though. So I'll just write the answer is the area is approximately 3.43 is what I got. But I don't want to take too much time going through the details of this one. We will with the next one though. All right, for our last example in this section, we're finding the area between y equals x cubed minus x and the x-axis. And for this one, again, we're going to look at a sketch of this graph. And what's kind of interesting If you factor this guy out, you get x times x minus 1 times x plus 1. And the reason that I'm kind of just like throwing that up there is that this graph, when I draw it, it has a point of intersection with the x-axis at -1, +1, and 0. And then when you draw the graph in here, the rest of the curve kind of looks a little bit like that. There we go. Cool. All right. And so this graph absolutely has some symmetry to it. And it says in the problem, find the area between that curve and the x-axis. And we can kind of see down here is we have a little bit below the x-axis. And what we see over here is we got a little bit above the x-axis. Okay, so that's what we're finding the area of right now. And what is kind of interesting and what happens here is if you just evaluate the integral, the integral from -1 to 1 of x cubed minus x dx, if you go through the steps, you're going to get 0. And the reason that you're going to get 0 there is this negative stuff down there, that negative area, cancels out that positive area up there. And you just, like I said, you just get 0. Okay? And the way that we can kind of compensate for that so that we don't get 0, because there is area there is stuff there, is we're going to say, all right, let's instead of doing that all in one, we're going to break this up into 2 pieces. And remember our top minus bottom. Okay, so over here in the left region, the left hump there, if you will, our bounds are from -1 up to 0. And then if I draw my rectangle in, although my picture is a little cluttered, it is from the function x cubed minus x down to the x-axis, so that we can evaluate that piece right there. All right, and then we're going to add to that another integral representing this region over here, only the difference is the top of the region is not the curve. The top of the region is the x-axis. Okay, so what we do differently there is we're saying, all right, our bounds are from 0 up to 1, but the top of the region is 0, y equals 0, and the bottom of the region is the curve x cubed minus x. And that flips all of the signs in x cubed minus x. So we go area equals x to the 4th over 4 minus x squared over 2. And that piece gets evaluated from -1 up to 0. And we add to that, when this guy all simplifies, 0 minus all that, you have a negative x cubed and a positive x. So when we take that antiderivative, it becomes x to the 4th over 4, that's negative, plus x squared over 2. And that gets evaluated from 0 up to 1. Check this one in your calculator. I would use that for all of the substitution, especially, if you struggle with all the minutia, the details there. And for this first integral, the first substitution, you get 0 for the top bound minus -1/4 for the bottom bound. And then for the other one, we get 1/4 for the top bound minus 0 for the bottom bound. And 1/4, because this one's positive, plus 1/4 is 1/2 for the area of that region. Okay, so that's how we can compensate and not have the negative area cancel out the positive area. Thank you very much for listening. Get to work on the homework problems for this section. And as always, please let me know if you have any questions. Thank you for listening.